All right, so I guess I was asked to do the planetary tectonics part 2. So let's see what is going to happen. It's going to be about Mars this time. We learned a lot from Venus about the type of feature we have on Venus, and we'll see some of them are going to be seen on Mars again, but not everything. It's okay to think that eventually the rate at which tectonic activity happens on Mars is less than it does on Mars, on Earth or Venus, and that makes sense because, of course, the planet's been much smaller. There's less heat overall. It basically stops being active much earlier in the past. So instead of having everything over the last 500 million years, you basically have most of the activity over the first billion years of history of Mars, maybe 2 or something like this. And it's going to keep on going at a very slow rate after that. That doesn't mean there is no tectonic features to be seen on the surface of Mars. Mars is much smaller than the Earth, but the surface area of Mars is about the same as the continents on Earth. And so you have plenty of geology to go around. So let's go and see a few things. So like I did last time, we're going to move to Google Earth. So this is the view that we have Venus. So I'm going to turn off the Google Venus layer because that's now the Earth, all right? And for Mars, things are simpler. There's nothing to download. Just go here on that little planet there, and you go to Mars, and it automatically uploads a bunch of stuff. Google Mars so that's a native Google Earth feature. So if you go to those layers down there, you have all kind of information, and I'm going to turn off the rovers and landers because that's too small for me. And you can see here the type of, what's great about it is that they already bring you a lot of different types of data sets that would be available here. Now, if you know a little bit about Mars, you know this is Viking, things from Tempe, etc. The ones that I'm going to mostly use are actually the Viking mosaic map, just because it's fairly uniform over the entire planet. And what we call colorized terrain, which is really just the altimetry from MOLA, the laser altimeter that was on Mars Global Surveyor, and so that's really the shape of the planet. But it's a pretty good resolution, higher resolution than what we had on Venus, and so we can see things very well on it. Just to give you an idea, some of the higher resolution images are where you have this CTX, that's context imager stuff. And you can see the problem is that it's only in a few places on the planet, so that's why I'm not going to use that, generally speaking. But instead, we're mostly going to look at the Viking layer because now we have about the same resolution everywhere. Now, we don't see very much right now, so let's go see the first things. So, for example, let's go check the Wrinkle ridge is in this place called Hesperia Planum. So diving in, and when we get very close to the surface, we see those stuff in there, all right? These things are what we call wrinkle ridges, and they are interpreted as thrust faults, so evidence for compression, basically, along this direction on the planet. Unlike the graben that we see on Venus, you can see that they are having some sinuous, they are much more irregular in their outline. And one of the things, sometimes you have this kind of an echelon pattern of it. It is topographic high. I mean, you can see that from the shadow. That now this time, because this is an actual visible image and not a radar one, the brightness and the darkness are usually correlated to elevation and slope. So you are very flat, you go up a bit, and then you go down a bit. And what you see also is that it's flat again, and that there's not a drop in there. So that's actually very interesting. We'll come back to what that means. One of the things that we have on Mars, which is great, is, like I said, the topography. So here is a topographic image. Sorry, it shows better on the screen. And you have, just shading the topography, you can actually see the object itself. And for that, you really need a high-resolution topographic data set, which we don't have for Venus. And that's really something that is missing. The interpretation of these wrinkle ridges, thing that I actually worked on personally, is basically that you have a thrust at depth, and that would produce some kind of anticline on the surface of the planet that makes the ridge. And there is potentially a back thrust that happens there that makes this like little wrinkle there. So here you see the ridge itself, that's the whole width there, and the wrinkle, which are here. And so this structure, we think at depth there is thrust. One of the big questions on Mars is how deep that thrust is. So we saw Hesperia Planum. Let me go back to the Viking images, and let's go to another one that's called Hesperia Planum. Yeah. It's on the other side of the planet, so don't get seasick while we're moving on the way, but it's all right. what you see here is a plane which is riddled with these ridges in two different orientations. That's quite interesting already. And sometimes you see this circular stuff, which, just like this morning with the Caltech symbols, it really are circles and not, ellipsoid. And basically the idea is that those are probably, although we don't know for sure, these are probably ancient craters that have been buried and are now guiding using as stress guides, and you have the ridge developing on top of that. So that would tell you those ridges can't root too deep into the interior of the planet. One thing I want to bring up right away, as we're having an image like this plane is covered with wrinkled ridges. And when you have planes of that age, that's called a Hesperian on Mars, that's usually the case, that they're going to be covered with wrinkled ridges. And so just like on Venus, we basically had this idea that you put a lot of planes and then you contract things, make a lot of wrinkled ridges. The same story just might have happened on Mars. We don't know if it's a global contraction of the interior, if it's related to climate or something like this, but it looks like there's a time when you do a lot of those ridges everywhere. Okay. Whoever.
When I moved over here.
You have these shadows from each of these craters. Is this real or?
Yeah.
Yes.
Absolutely. That's the shadow. These images are the best ones that are put in this mosaic. Usually has a fairly low sun angle so that you can see the relief better. And I mean, some not in here, but in the previous view that I had, we actually could see places where the mosaic is at different conditions and things like that. They try to keep the better ones, the cleaner ones. Yeah, I think.
On that note, not the shadows, but the white, the light colored. Is that wind or the?
Oh yeah. So visible images, of course, it's not all shadows, right? I mean, we don't need a shadow to see a different color on the top of the wall and the bottom part of the wall, right? There's brown versus green. The same thing should be happening on Mars. You will have region where the ground is inherently a lighter color. So yes, these are albedo markings. I can't know that for sure just from one image, but most likely that's the case. And yeah, from the look of it, looks like there's probably a dominant wind direction and places which are more or less dusty, something like that. Bill, I think you can finally have.
That was all related.
That's the thing. If you don't let Bill ask the question, eventually the question will get answered before he asks. Sorry. I'm going to show you one more region of wrinkled ridges, because that's one that really brings home the point to me that the topography is important. This is in the northern plane of Mars, which are pretty young, younger than the rest, although the age of this is pretty much the same as the other planes that I showed you, this Hesperian time. And if you look in Viking here, you don't see much at all. There may be a ridge here, but you don't see anything at all. And one of the big discoveries from Mars Global Surveyor, the topography was, no, not that one, this one. Once you actually take a topographic data, you can actually shade it, and you see that all of those things are essentially old ridges have been covered by a layer of dust. The visible image, you can't see it, but you actually have the topographic expression. So once you look at this, the global tectonics of Mars, you have those ridges at a certain period of time. Virtually everywhere you have terrains from that age, you have wrinkled ridges on it. I'll come back to the global arrangement of things. It's not, but before I do this, let me just move to another place called Tempe, Terra, which is on the northeast part of Tarsus. We'll see what it is. I'm going to go very quickly on it. This is, again, from the topography, but you could see that in Viking image as well. It shows actually now these fractures here. Those are essentially rifts, the same type of thing as we have on Earth, as we have on Venus. You can see it in this case. It's, again, dated probably from about that time. The ground here, it's probably a little bit older, but you have dates of the tectonic activity, which is, again, from that magical Hesperian time. This is a rift which is not exactly like the Earth one. There's actually two rifts here, the Tempe rift, which you see in here. And that has some big normal faults, so everything is fine, except that maybe they are a bit longer than what we tend to have on Earth. And then there's the Mariolis Fosse rift, which is basically all these straight lines there, and those are very small, very narrow graben, so not really something which is similar to what we see on Earth. So you have evidence of extension, but not always accommodated as something that looks like a continental rift. One thing about Martian tectonics, whether it's the shortening of the wrinkled ridges or this evidence for extension, you only have a few tens of kilometers of extension on those structures. So you never have plate tectonic like, thousands of kilometers of divergence between point A and point B. It's always limited by the best of what we can reconstruct here to a few tens of kilometers.
There's this transition from rougher topography to the north to smoother topography to the south in one particular place with a almost east-west sudden transition.
Yeah, are you talking about this here?
No, just to the right.
This?
Yeah, no.
Here?
Yeah, this.
Should remember to always bring the pointer. Yes. Right. So all right. On Mars, you can see 3.5 billion years of history. And at that stage, you actually can see difference in terms of the texture of the terrain just because a 3.5 billion year old terrain has had a lot of impacts on it, whereas a 1.5 billion years old terrain didn't. So you actually have these blocks probably of fairly old rocks that have for some reason or another been uplifted. Eventually, you probably were covering this with some plains later on that looks like early Hesperian, kind of just eyeballing it. And the whole thing has been deformed later on. So basically, this is several episodes of geological history, some old stuff which is high standing here, and then these guys here. I mean, you can see those structures here seem to be truncated there. So there is definitely a history of events on Mars in many places that you look at. And I'm not going to say that this is internal structure or if it is an impact or anything. I'm not going to go and speculate on this without looking in details, but these are things that you would want to consider. But if I'm zooming out, something that's going to look a little bit more like Venus is that this region with the rift is also kind of a fairly circular, high elevation region. So it's a little bit like what we had in Beta Regio, a rift on top of some potential upwelling or something like that. Now, if I zoom out some more, we see the big guy, of course. Stop. Tarsis. The Tarsis Volcano-Tectonic Province, or Tarsis for short, which is really the center of all of the activities, or most of the activities we have on Mars. The planetary radius is in these green colors, roughly, and you have this gigantic pile which covers a quarter of the planet, something thought to be huge amount of volcanic thickened crust, and you have, of course, the giant volcanoes on it. The Tarsis Mountains, Olympus Mons, the one that every textbook says is the largest volcanoes in the solar system. Alba Mons, the one that actually is by volume, and so, not in elevation, but by volume. It's so much bigger, etc. So you have a lot of activity here, and some pieces are very old, and some pieces are essentially zero age, like in the center of these calderas of those volcanoes. So we know that thing's been active for most of the time. And we know this also for another line of evidence, which I want to show you. Oh, I didn't know it was going to keep on doing that. Sorry. These used to be hidden. Now they're not. Anyway, some of the work that people have done is, so this is a map of pretty much the same view as what we had before. And every tectonic lineament that Pavanelson and a few others have mapped on the planet, broken down by their age, but it's all pretty old stuff anyway. And what they found is that usually these seems to be pointing out or being circumferential to a center of activities, which over time moved from here to there, to there, to there, to here, but always kind of somewhere in the vicinity of Tarsis. So on Mars, it's fair to say that all of the tectonic activity is not forming one of those global networks like what you would have for plate tectonics, but it's all centered around something which is related to Tarsis. I should also say that evidently the uncertainty, each one of those points could be a 100-kilometer wide ellipse or maybe even more than that. Another thing which is important, and I talked to someone earlier about this, is so you have regions which are undergoing extension, regions which are undergoing compression. Oh, I forgot to show something, but that's fine. And we have this central of activity. In fact, you can already see here, those are maps of the Wrinkle regions, and you can see how they are forming some kind of arc, all right? And then you have regions of extension that seems to be radiating away from the center. Now, the topography of Tarsis is huge, and it's centered about there. So people have done some model of elastic flexure, just saying we have this pile of volcanoes, thickened crust on top of a spherical shell, which in this case would be 100 kilometers thick, and they calculated what would be the strain. The direction of the strain is, of course, by the little bars. The magnitude of the strain is by the colors that you see there. And essentially, this simple model, you take the topography and gravity of Tarsis today, you take a 100 kilometer thick spherical shell, and you can match the orientation of most of these features. So really, in terms of global tectonics, Mars is Tarsis. And that's pretty much what you have for most of the planet. And the other thing is, because of the age of these things, you basically know that Tarsis had to be present pretty much in its current state at the beginning of history. That is 3.5 billion years to Noachian. You needed a load that, if it's not the one that we have today, was very similar to the one that is today. So, of course, the simplest answer is that's the same thing, right? So, to produce these type of structures. Last, you had another question? No. So anyway, this is just to say you that global tectonics on Mars is essentially Tarsis. I will probably just... Any questions on this? I
Also, why don't it goes green to speak? Because the reason they have no effect is because most people are speaking when it's red, the light.
The Yin paper that you were citing on that previous, I thought they argue, or he argued for plate tectonics on Mars.
Yes,
is that correct?
That he does.
And
I wouldn't.
Okay.
And I actually have a couple of slides that I can tell you some of the reason for that. But actually, let's talk about some of the things. Okay, so yes, there was a paper that was published 2 years ago. The title is something about plate tectonics on Mars. And plate tectonics on Mars, well, okay, I might as well just go there because this is one of the things. It's an idea that won't die. There have been a lot of evidence that was proposed over the years repeatedly for plate tectonics on Mars, and I think most of they really didn't spend wow, it's dead. Sorry, there's an expression which escaped me. For example, back in '94, Norm Slip did a very nice paper where he basically said, okay, this could be actually like a volcanic arc, those guys which are aligned there, and why not? One of the issues was that then, okay, and you can see this, but on the other side, the planet, it's pretty low elevation, so he said maybe that's an oceanic plate and you have a subduction zone there. But if that's the case, you would have, transform faults there, and yeah, there's a scarp, but that's not really a transform fault. You would have a region of extensions never been found. You don't know why you would have this guy there, etc. So there were always a few issues with the issue, and in fact, the very next year, he was co-author of a paper saying, that's a nice idea, but it probably doesn't work. Okay, himself was a co-author on that. So, but that doesn't prevent people from citing it as evidence for plate tectonics. And it's really, that idea is, it's really dead because it turns out, now that we have the topography, we see a lot of buried old impact craters in that region. And basically the age of that place, although it's low standing elevation, is the same as the rest of the planet. So it's not like you had really a later on crust that showed up there. Mars Global Surveyor had a magnetic things, able to detect magnetic anomaly at the surface. Some papers show them as very nice long stripes. Yes, they are a little bit elongated, but not nearly to the extent that we see on the map. There was a bit of a map projection issue on that place. And they are not really symmetric. They don't really look like a terrestrial magnetic anomaly. I don't know what makes them, but it's probably not seafloor spreading. Plus, it was very much on the wrong place for seafloor spreading in terms of the geological environment. And then, Onion had recently a paper where he's talking about the tectonic on Mars. And one of the evidence, actually, he had two papers in the same year. Both of them are 50 pages long. So, but anyway, one of the thing is, this is Valles Mineralist, famous as the Grand Canyon on Mars. And that's actually a very good description of it because just like Grand Canyon on the Earth, this is mostly an erosive feature where you had basically underground water flows that are basically, it's erosion essentially. So you have material that's been transported thousands of kilometers that way and then make it that direction. It's basically some of this material that is covering the northern plains on Mars. So Yes, it does have a tectonic origin. You can see some cracks and things, and if I zoom in, you will see that, yes, indeed, there are some cracks in there, but it's mostly an erosive feature. Anyway, the point that, and one of the things Anne does very well, is to demonstrate that it's quite possible there is strike slip going on in that location in here, and that would be left lateral strike slip. And that probably is the one place where I would say you have several hundreds of kilometers of displacement on Mars. And part of the thing is this break here might correspond to this break there. There's some magnetic boundary which seems to be here and there. So there's some evidence that you could have a couple of hundred kilometers of displacement on that structure here. Yes.
Is there any estimate of how long it would take to make that feature? How long we would have had to have flow?
That's the estimate.
How does it get that big?
Okay,
and that
it's
deep?
just that what I'm saying is that it's geologically instantaneous, because what happened is that you have these giant outflows, okay, that are catastrophic floods, okay, which are coming out in this direction here. It's not very tectonic, so I didn't intend to talk about it, so I didn't make a place mark. But if you look in here, you see all of those big river stuff, river-looking things. You have streamline islands and things like this. This looks like, for example, evidence for the big Missoula flood erosion in Washington State, where you had this glacial lake that just burst and flooded through and was able to erode the bedrock and things like this. This is probably what we had there. So there's been estimates of the rate at which the flow has been going on, and it's just crazy. It's larger than any flood we have on Earth by far. But that's what you would need to actually carve the ground the way we see it there. So that's why I'm saying, geologically speaking, compared to all the other processes we've been having there, it was instantaneous. So you must have some big cracks, a big reservoir of underground water, and then the whole thing goes. Chris?
I was just going to ask you where all the water came from.
Underground.
Yeah. Just another question. The volcanic region you showed us just a moment ago is really, really big.
Yeah.
And yesterday we heard about the influence of changing surface temperatures on Venus on a global scale. Is the thermal load from something like this significant, or is the time scale over which it's in place too large, too long for something like that?
Well, I'm trying to think what is the time scale over which it was in place. I mean, the bulk of it is very early on, but there still is 500 million years probably. That's the resolution you have. These guys are huge, but don't get fooled. These are just the veneer on top of things. Talking about a 10-kilometer pile of veneer, but whatever. The bulk of the mass is probably very old, and we know that from the stress field. We know the temperature, the climate was different at that time than it is today, and there has been some discussion that maybe the outflows and the volcanic activity of the very early Tarsis was somehow responsible for making a lot warmer, wetter climate on Mars back in the Noachian. So it could have done this. In terms of thermal load, I don't know, but maybe that's something people can calculate. Louis?
I have a poorly formed question.
There is no poorly formed question.
We'll see about that. Okay, so you've got that big volcano, Olympus Mons, right?
Okay,
and
sure.
it looks like, or any of those, they look like Hawaii superficially. So they are, but Hawaii being part of a chain, so the standard model is the plate moves away and you get kind of refreshing of that every so often. Mm-hmm. So in this case, if you were to build this in the same way, you would have an increasing load on the planet on that spot. Mm-hmm. And wouldn't that, for the petrologists in the room, wouldn't that change as you increase the pressure on the upper mantle? You have this upwelling plume, supposedly, that is erupting. But shouldn't that, it's going to erupt, and then there'll be some depleted part, and then what happens? So you're going to build stuff from the top, and you're going to accrete some stuff from the bottom, and then how do you keep getting more and more melting to build this enormous shield volcano instead?
I think that's a problem. But
is that a problem? Has anyone solved that problem?
No.
Is that a project for this group?
Projects are driven by the junior members.
I propose that it be put on the list of projects.
I mean, there's been some ideas
just to see
about,
what the
when you make
limitations
that
are.
load, what does it do for the state of stress in the lithosphere?
Yeah, but
That's
there's
been
also
looked
the
at.
petrological part of it that you,
Yeah,
bring,
I mean-
let's just assume you have the amount of heat you need, but you still
Right.
are going to be then
For example,
changing.
on Earth, right, Maxim Balmer has been doing some work recently about having the depletion of, the atmosphere underneath the Hawaiian plume and how this may affect the dynamic of the plume. There has to be some effect in there.
And here it doesn't get moved away by plate tectonics.
Here it doesn't get moved away. That's how you get such huge volcanic piles. As someone calculated once the volume of these guys and compared with the entire Hawaiian emperor's chain, it was comparable.
So instead of being a kind of steady state project, process, which you can think of Hawaii as the Hawaiian chain as being, it's a transient, it's a chain, it's a time variant.
And it gets worse because, of course, this guy is on top of that volcanic pile.
Yeah, that's right. But even ignoring that, it's still
Even ignoring that, just one plume, how do you keep going? That would be a lot of fun. Ben?
Actually, just a comment on Louise's question. I think Baratu has looked at the chemistry, like the iron-magnesium ratios over time, and seen some trend that he associates with gradual crustal thickening.
I just heard iron-magnesium ratio and trend and crustal thickness. So can you repeat it louder?
I get if Louise's question was, are there trends associated with the thermal evolution of Mars? I think people have tried to look at that a bit, like looking at the iron-magnesium ratio from orbital data, and then inferred that you had lower degrees of partial melt as the crust thickened.
Michael tells me it's not a problem.
It's not a problem to keep the plume going?
Well, I guess I should use the microphone.
Yeah, let's record that one.
So in order for melting to occur, you have to deliver hot material close enough to the surface to melt. And we know mass is conserved, right? So if something is coming up, something has to make space. And so there has to be lateral flow from that plume to accommodate more material rising. And so anything that's depleted by melting
the
is
problem
moved to the side by the plume rather than by plate motion.
The problem is the residual being buoyant may not be happy to move on the side.
But it must be. But it has
I mean, it has to, but the dynamics are actually not trivial.
So why? Pushing out this buoyant material?
Okay, fair, because, so the first thing that comes to mind when you say that is that then the result would be that you would have a point and then you would have kind of a circle of activity, which is not what we observe. But we do see the center of activity migrating over time, maybe this way, that way, etc. So you see it moving around. So that would be actually a really fun thing to do, is to see how the progressive depletion may actually move, Shigeru Hachong actually done some models where you have a plume and you have gradients in lithosphere and things move around, and now the plume is at the surface somewhere else, right? Moving the entire lithosphere. This could be done here in terms of explaining this progressive, the motion of the center of activity. That would be a lot of fun to do that, actually.
And in the last issue of JGR, one of Scott King's students, and Scott King, said that the thickness of the crust varies monotonically as you go north, arguing that there's also migration of volcanism in that direction, whose record is preserved in the thickness of the crust.
But that's also probably related to the difference in the dichotomy, which I didn't even want to cover here, but yeah.
So I'm going to think about this in a fairly simple way. A lot of magnetism on this hemisphere. I guess not much or none on the other hemisphere. Is there not much or?
Do you want me to give you the standard gospel or some crazy idea? I mean, you have this beast here. It's a small one.
Okay.
And if you look here, you have a big crater, right? Hellas. That is the blue hole there.
Mm-hmm.
If I'm moving here, that's another big volcano and a big volcanic plain. It's
so
just very flat, but it's older. It's not as big, but
so I'm going to get carried away then. I'm going to say that one hemisphere has a lot of heat being expressed out of it, and the other hemisphere has less heat coming out of it. Then I've heard, ideas like plumes. Okay, so then I'm going to suggest that they are coming from the core mantle boundary. They could come from other boundary layers, but let's just go with this idea. Does that tell us that there's massive differences in the structure maybe the physical expression of the Martian core. Behind me, there's some female voice going, mantle, mantle, and take over.
You can take it.
No, I can't really. You can explain. So C.G. Zhang's done work on this, and in which, I'm going to forget the details of this because it was a while ago.
The degree 1 convection stuff?
Yeah, but basically you get degree 1 convection in the mantle of Mars, is what you can get degree 1 convection in them.
Based on the size of the core.
Based on the size of the core and where the phase transitions are located, essentially. The key is the viscosity structure, says Michael. Mm-hmm.
So what does it mean for the core? I don't know.
Okay.
I want to ask. So you were saying it has to do with the viscosity structure. Doesn't it also have to do with the height of that viscosity transition above the core? So for those who might not know, we don't know how big the core of Mars is, but based on the pressure increase on Mars, which is less than on Earth, the core radius is somewhere around where you switch over to perovskite. So there may or may not be that layer. And if you put that layer just slightly above the core mantle boundary layer, you get a thin layer of relatively high viscosity, and that acts as a low-degree filter on the convection. Very simplistic view there.
But there's been
That's
some
a non-geodynamicist saying that.
There's been a little bit of issues on that in terms of the time scale it requires to actually develop the single plume and things like this. So this is not a soft problem as far as I can see, that you actually can make a plume of degree 1 in essentially less than 1 billion years, okay? Because if Mars is that old, which we think it is, you have to have the plume developing very quickly, and that's very difficult.
But to summarize, essentially the thinking is that that degree 1 convection is possible on Mars due to the structure of the mantle, not really due to the structure of the core.
Right, and going back to what I think Bill was saying, well, I don't know what you meant by structure of the core, but there probably would be some effect on the way that the core is losing its heat, right? Because if it has one big plume coming from there on one side, you're going to have some interesting effect there. I think that's where you were driving at. And I don't believe that's been explored, but then again, I've already showed several times this week, I'm not up to speed on all the literature.
So I'm not wrong. I'm not wrong when I'm thinking along the lines that people talk about for the Earth, that is the core heat flux is expressed by plumes. So that's where I was thinking also. Right? And that to me seemed funky because it's expressed on one side of the core.
Okay, let's move on maybe because time is going on. Yeah, I can conclude. I conclude there. It's concluded. Plates been tried, proposed. Let me just show you the one place where there is one of the things that worked recently. Oh yeah, the in thing, there was some serious timing issues. It was talking about rollback progressively starting and basically having subduction for a while, stopping and then restarting. There's all kind of mechanical issues with that. I also want to show that the one part where basically a plate has been defined on Mars would be here, Solid Planum, where you would have this left lateral motion here. You would have compression along this fairly high rise there. You have extension on the back there, and whatever happens here, people can't agree about what's going on here. But anyway, you could imagine that you have one place that is kind of moving somewhat. But even these people didn't really call that a plate because it's deforming internally and it's very limited in terms of motion, so they were more thinking of a big landslide on the side of the planet. I've done a bit of work on it, and there's some issues about the friction of humidity at the base. But at any rate, if you want to find a plate on Mars, that's what it is. But for all the rest, you really want to think about center of activities and things, essentially radial or concentric around those center of activities. And that's it.
Fairly detailed maps of magnetic stripes, paleomagnetic stripes preserved on Mars. Is that controversial? Or I know there's some spots where there's no paleomagnetism preserved. A dynamo existed and then turned off. But the interpretation of those stripes I've seen that look very plate-like. Has that been discounted?
That's been discussed. I don't think that I wouldn't say that the community has come to an agreement about what really is going on to form those stripes, all right? So you will always find people who will think that it is indeed kind of a spreading center type of ideas. There's been ideas that you have big swarms of dikes that are that have been intruded in the crust at that moment and would have taken whatever the magnetization was. Where I have really big problem is that to know any of those stories, you would want to have some geological evidence at the surface, and that's missing. So it's pure model, essentially. But for example, Michael and some of his colleagues have done some great work, especially on the demagnetization issues and whether it's possible to do it with further intrusion in the crust and stories like this. There's clearly are some times where there was a magnetic field on Mars, and we have it recorded typically in the older rocks, and at some point it could not have been there anymore. That I don't think is controversial.